Video 55. Video 55. Third problem. Using induction, prove that 1 squared plus 3 squared plus 5 squared plus etc. plus 2n minus 1 the whole squared is equal to n into 2n plus 1 into 2n minus 1 by 3, n greater than or equal to 1. n greater than or equal to 1. Proof. Let what you want to prove be the statement P of n. Let P of n colon 1 squared plus 3 squared plus 5 squared plus etc. plus 2n minus 1 the whole squared equal to n into 2n plus 1 into 2n minus 1 by 3. Then we have to list out what is P of 1. So starting with this 1 to 2n minus 1 is n terms are there. 1, 3, 5, 2n minus 1 means there are n terms. 1, 3, 5, 2n minus 1. Square is of course there. Now last term L is equal to 2n minus 1. Right? You know this is an arithmetic progression. L formula is a plus n minus 1 into d equal to 2n minus 1. What is the value of a? First term. Capital N minus 1 into d. D is every succeeding term is 2 more than the preceding term. 2 equal to 2n minus 1. So this implies 1 plus 2n minus 2 equal to 2n minus 1. 1 minus 2 is minus 1, cancel with this minus 1. So capital N is equal to small n. Therefore the number of terms here is, there are n terms here. n terms are there. 1, 3, 5, 2n minus 1. If small n terms are there. P of 1 means there must be only one term. On the right hand side put n is equal to 1. 2 into 1, 2 minus 1 by 3. What is P of k? P of k is 1 squared plus 3 squared plus 5 squared plus n is k. 2k minus 1 the whole squared is equal to k into 2k plus 1 into 2k minus 1 whole divided by 3. P of k plus 1 is 1 squared plus 3 squared plus 5 squared plus etc. plus k is k plus 1. 2k plus 2 minus 1, 2k plus 1 will come. 2k plus 1 the whole squared is the last term equal to right hand side k is k plus 1. K plus 1 into 2 into k plus 1. 2k plus 2. So you will get 2k plus 3. Here k is k plus 1. 2k plus 2 minus 1 is 2k plus 1 divided by 3. So this is very important things. We will have to write these three terms. Now we have to start with basic step. Basic step. LHS of P of 1 is equal to only 1 squared, which is 1. RHS of P of 1 is equal to 1 into 2 plus 1 into 2 minus 1 by 3. 2 minus 1 is 1, 2 plus 1 is 3, you get 3 by 3 which is 1. So this implies LHS of P of 1 equal to RHS of P of 1, which implies P of 1 is true. This is the basic step. Next we'll have to go to the induction step. Induction step. Assume that P of k is true. that is p of k 1 squared plus 3 squared plus 5 squared plus etc. 2k minus 1 the whole squared equal to k into 2k plus 1 into 2k minus 1 whole divided by 3, equation number 1. Now using this equation number 1, we will have to prove the validity of pk plus 1. So LHS of p of k plus 1 equal to 1 squared, 1 squared, 3 squared, 5 squared plus what is p of k plus 1 ending with 2k plus 1 the whole squared, that's all, equal to 1 squared, 3 squared, 5 squared plus etc. plus this is 2k plus 1 whole squared. Previous term, see 5 means previous term is 3, 2 less 3, 2 less 1, 2k plus 1, 2 less means minus 2, so you will get 2k minus 1 the whole squared plus 2k plus 1 the whole squared, and this value is given by equation number 1, k into 2k plus 1 into 2k minus 1 by 3 plus 2k plus 1 the whole squared. Now we can take 2k plus 1 as common into k into 2k minus 1 by 3 plus another 2k plus 1. This is 2k plus 1 into, take 3 LCM, you will get 2k squared minus k plus 2k plus 1. This is equal to 2k plus 1 into 2k squared, 2k squared. So when you take LCM 3 2s are 6k, 3 into 1 is 3, 6k plus 3, so 2k squared plus 5k plus 3 whole divided by 3. We are going to factorize this. Product is 6, sum is 5, product 6, sum 5, so 3 2, 3 plus 2 is 5, 3 into 2 6, so this is 2k squared plus 3k plus 2k plus 3. Here k is common, 2k plus 3, here 1 is common, 2k plus 3, which is 2k plus 3 into k plus 1 is the factorization. So 2k plus 1 into k plus 1 into k plus 1 into 2k plus 3, 2k plus 3 whole divided by 3. Is it our right hand side of pk plus 1, or which is k plus 1 is there, 2k plus 1, 2k plus 3, or hs of p of k plus 1. Therefore the conclusion is, therefore p of k plus 1 is true if p of k is true. This is our statement 2. P of 1 is true, we already proved. So result statement 2 is, whenever it is true for k, it is true for the next integer. P of 1 is true, therefore by 2 next integer 1 plus 1, p of 2 is true, p of 2 is true, p of 2 is true, therefore by 2 next integer p of 3 is true, etc. P of n is true for any positive integer n. So this completes problem 3 and also video 15.